Now to start this video, I want to show you this control unit working. That way we can then go into the details on how it exactly works. So right here I have my clear and my reset, and I warned you that you might have done another reset in your data path because I had one up here that I have deleted. That way I have one master reset switch that will clear everything. It'll clear my my buttons that I made, and it will also clear everything out in my state machine that we'll learn about today, and also all of the registers. So now I'm going to go ahead and automate this clock. So I'm going to enable our ticks, and I'm going to have it move somewhat fast, but not too fast. And now you can see that my clock is oscillating or alternating between high and low automatically. So we know that our control unit works if we hold down this start button, and we keep holding it down for a while. And we're going to look at this wire right here to see it go high for one clock cycle once I release the start button. So I release it, it goes high, and now my machine starts. And notice after that one clock cycle, it's back to 0. And so now we see it going through our states. So hopefully you've seen other videos and you've been studying that fetch sequence. So the fetch sequence is it goes 50, 51, 52, 53. So in 50 is our step 1 of the fetch sequence, 51 is step 2, and 52 is step 3, and then 53 is the decode stage, where we're going to look at our IR register that and figure out what the opcode is for that IR register. And then once we have the opcode and know what it is, then we'll go ahead and jump to the instruction, and we'll execute that instruction. Now I updated this to look like what you would have copied and pasted out of your control unit. And this is a pretend IR register. It's really just a switch turned into 16 switches, just an input switch. Right now it's pretending to be the instruction register. So on state 50, 51, 52, we do the three steps that you hopefully did on the quiz that fetches the instruction out of memory and puts it into the register. So again, step 1 is PC to MAR. Step 2 is memory to MBR, plus adding 1 to the PC. And then step 3 is taking the MBR into the instruction register. And now we can put an instruction in here, and a pretend instruction in here, because it's just pretending to be the instruction register. And then on step 53 is the decode stage, where it's going to figure out what instruction it got out of memory. It's going to figure out what it is, and then it's going to go jump and execute that instruction. So back at our programmer's reference, we see that an add instruction is 4 ones at the top plus 6 zeros at the bottom. So we could go ahead and put that into our instruction register. So right here, and you kind of have to be quick. If you notice, my control unit is running. It's kind of running slow, so it does give me a little bit of time. But if I put in an invalid opcode, this will get into an error state, which is okay. I just need to turn on my reset everything, and restart it again to get out of that error. So really we're going to do the 4 ones at the top. And now we could see that our control unit goes to different states. Right here we have 50, okay, so 50, 51, 52, 53 decode. We know it's an add. We execute the add. We're back at 50, 51, 52, 53 to get the next instruction out. Of course, I didn't change the instruction in my pretend IR register. So let's go look at another instruction in our programmer's reference and put that in there and watch our control unit execute that one. So we can see that we have a load high immediate, and that only uses the top 4 bits, and our opcode is 0110. So let's put that into our pretend instruction register and see what our control unit does. So, and again, try not to time it so it's happening around state 53 right there. So I wait until after 53 to execute this. But now, right here, we have 6, and notice now we got a different instruction that it's loading out, and it's following a different path. But after it executes that instruction, it always returns back to 50, 51, 52, 53, right there. We're going to do one final instruction, and that's the halt instruction right here. Now, if you notice, the opcode is all 1s, which means that we're also going to use the function code. So while it's executing the low-high immediate right now, it's not going to look at the function code. So I can feel free to change this. It won't affect it at all. And then I'll go back and turn the opcode to all 1s, and then we'll execute the halt instruction. So you can see I put the function code in the bottom bits right there. I'm going to make sure I time this away from state 53. I'm going to put all 1s in there. And now we're going to execute the halt instruction right there. So now you can see we're kind of stuck in state 2C. And if you just reset everything, that's the state you're stuck in. So this is the stop state. So how do we get out of that stop state? Well, we press our start button down. We release it, we get the 1 clock cycle start, and now it fetches the next instruction out, which is a halt instruction. Now it's back in the halt state again. So that's how our control unit functions. So let's talk about all of these different pieces, and I'm going to bring up a diagram where we can talk through this. Now the first diagram I'm going to bring up is on this page right here. You might want to go to it yourself so you can see the full page. But this is, on this page, we have a big finite state machine, or a state machine, just like the one we built, you built for your button, and the one we built in the other video. We just have a state machine. The only thing is this state machine has a lot of states. We're lettering our states instead of numbering them this time. So we have A, B, C, D. And that is, our fetch. If you notice the 4 or the 3 steps that I'm having you memorize, this is step 1, step 2, step 3, and then in this state right here, we decode and we branch to execute whatever instruction we loaded out of memory, and we branch to that instruction. And it's so big, it's hard to fit it all in one picture, so we go to state E, and then down here we find state E, and we execute that. And we go down, and this at the end, it tells us to go back to state A. So you can see that was what we're doing, except for the states were A, B, C, D. It was 50, 51, 52, 53. And then I believe it went to state F. Then it did 54, 55. And then it went back to A, which is state 50 again. Now, there's 2 ways that we can build this control unit. We can do exactly like we did with our stoplight example earlier in class. We can do that, but there's so many states here. We're going to have a lot of tri-state buffers. And now when we try to use our K-maps, there's going to be too many variables to use K-maps. Now, K-maps are not the only way to do it. There's other ways to simplify Boolean expressions. And so, and there's ways that you can write programs that will simplify the Boolean expressions. So you can build this out of D flip-flops, just like we built our stoplight example out of D flip-flops. It's just that we're going to have a lot more D flip-flops because we're going to have a lot of different states in here. So we're going to do a shortcut, and we're going to do a microprogram control unit. So in here, we have this this is actually the microcode right here. So I'll come back to this. But here is the diagram that I want to bring up to show you all the different pieces. Now we have the ROM. This is ROM stands for read-only memory. So that is what stores our micro program. That's all of this information is stored into this ROM right here. So this is our store right here. Up here we just have an address registers. It's 8 bits wide right here. That's what the 8 stands for. That means there's 8 wires along here. And out here we have a micro MBR register. So this is just like any other register, except for this one is 47 bits wide instead of our 16-bit wide register. And again, this one will be 8 bits instead of 16. We have a mux that chooses 4 different inputs. And so those are the different pieces. Now, if you notice our clock signal, it alternates clocking. It'll clock this register. This right here is a NOT gate. So that just makes sure the registers clock on different cycles. So this clocks on the up edge when the clock goes from low to high, and this one clocks on when it goes from high to low. So they just kind of alternate changing, and we'll talk about why that is. But first, I just want to show you where these pieces are on our diagram, or on our circuit. So right here is the mux in the diagram, and you can see it has 4 different inputs. Then right here, these two things combine because it has to be 47 or 48 bits. I think at 47 bits wide, and you can't just grab a memory that's 48. So I had to split it into 2. So here's our ROM right here. And then finally, these two guys right here are the micro MBR down here. So that's just that one register that's 48 bits wide. And this right here is the micro address register. And it's a normal register, just 8 bits wide instead of 16. But it also has a different feature when you reset it. Instead of going all to 0, it actually resets to 2C, which is our halt state. All right, so we have that diagram here, and what I talked about before, we have this NOT gate right here. So what that does is it alternates the time that this register changes and this register changes right here. So a normal clock signal just goes up and down like this. Of course, with the NOT gate, it will be the opposite, so it'll go like this. And so we got this guy right here. He gets clocked at these times, so it's the original clock when it falls down, because it goes through the NOT gate. That's when this guy gets clocked. So when the micro MER gets clocked. So that's this time. It gets clocked again at this time, and this time. And this guy, he follows the opposite pattern. He gets clocked here, here, and here whenever, so they're basically on opposite time. So the way this works is the micro MER is a memory address register, and the address that it remembers represents the current state we're in. So when he has state 50, and by the way, 50 is in hex, so that's why there could be state 0F, because F is a hex letter, and other states, so that's a hex address. But if we have a hex and 50 right here, then what that does is it feeds into our read-only memory. So read-only memory works like regular memory, except for you can't change it. So this control ROM looks up the data that he has at memory location 50, and he spits that data out there. And then when the clock comes along, the clock takes the information from the ROM and stores it inside of here. Now, the lower bits are control signals. Those are going to connect to all of your switches on your data path. But you don't need to do that for the control unit lab. That's the final lab. is connecting these control signals to your data path. So, that this, just in summary, this has the address or the current state we're in. That causes memory to look up what signal should be turned on in that state, and then when the clock comes along, the signals will change in here, which will turn on and off your switches in your data path. Now are some other information right here, and that's to try to figure out what our next state is. So right here, on that input, that's where the state we're going to go to next. Now there are four options on the next state. One is our start. So when we click our start button, we have the mux, we have some logic here that has the mux decide that we're going to go to state 50 next. So that's our start. This right here is for our decode, and this looks at the opcode and the function code, adds them together if both of them exist, and that becomes the next address. So if we add our opcode and our function code together, then that determines the next address or the next state we're going to go to. And then another option that we can go to is just go to the next state. That's probably the most common. That's why we see 50, 50, then the next state is 51. And we just add 1 to the state we're in, and it goes to the next state, 50, 51, 52, 53. Okay. This final option right here is like a jump, and that's how we can like jump to different spots. That's when we're done executing an instruction, we want to jump back to 50. So if we want to jump back to 50, we just put 50 right here in the MBR, and then that tells us the next state should be 50. Now these signals right here just affect this combinational logic that helps control the mux decide which should be the next state. Do we just add 1 to our current state? Do we decode our instruction over here? Do we go to the start instruction? Or do we jump somewhere in our code right there? So that's the basic idea of how the micro control unit or the micro program control unit works. Now the hardest part of creating this would probably be writing this microcode. Luckily, all of that has been written for you. So on this right here, we have the microcode. The one thing that might be a little bit confusing is these numbers are in binary, but the display on your control unit, that red number that went 50, 51, 52, 53, is in hex. So if you convert 50 in hex to decimal, you get 80. And so here's state 51, and it has the register transfer language, or what we want to accomplish, and it has what control signals we turn on in that state right there. So you can see that 50 has those 3 switches. 51 turns on these switches and these switches, and then 52 turns on these switches, and then 53 is our opcode. So, or our decoding of the instruction. And like I say, the way that we decode the instruction is we add the opcode to the function code. So if we look at our instructions opcode, right here we have the add, and this right here is 16 in binary, plus 0 in binary. Actually, this is 15 in binary, plus 0 right here, you get 15. And that is F in hex. So that's when we do an add, we go to F. Let's look at this next instruction. This is add immediate. In this case, there is no function code. Our opcode is not all 1, so we know, oh, don't add this here, just go to this thing right here. So if we look at our microprogram control unit up at the top, we could see that our add is at state 15. Versus add immediate that doesn't use the function code right here is at state 4, And if we look at our programmer's reference, this is for in binary right here. So all the instructions that don't use the function code are right here. And all the instructions that do use a function code are right here. Now if we happen to get any of these, then that's an error. That means we pulled some instruction out that just doesn't have a valid opcode or function code right there. Here are some other opcode and function codes that we use. And right here is our halt state, so that's 44 in hex is 2C right there. And you guys can look through this more and see how this jumps through this, or how our control unit works. Now you don't have to write all of this. We wrote all of this up and we put it inside of that ROM that you copied and pasted. So all of this should just work. So the only thing you have to do for the State Machine Lab is get that button working and put it on, and then make sure that you know how to operate the control unit 1 and then how it works as well. There is one last thing I wanted to cover, and that's why have a register down here? Why not just read the data directly coming out of the ROM? And that's because the ROM, as it looks up data, it could kind of turn on and off the signals really quickly as it starts to look up some data right here. It's not a clean switch from when it gets a new address on its input that suddenly it just spits out the right information. It takes it a while to get the right information out. And as it does that, it could be turning on and off some signals. That'd be pretty bad if we started turning on and off our clocks on our data path. We might erase the data inside of it. So while this thing is kind of flipping on and off as this looks up the new data, this register right here keeps a consistent state until this thing's done and ready, and then it just pulls all the new information into the new register at one moment. So that's how the microprogram control unit works. And so you might guess the last lab is just hooking up all of these control signals to our data path. Now you can see I've actually labeled all of those for you to make it nice and easy. All you have to do is connect them up. Now there are some things to talk about between now and the final lab on how to connect these up. A couple of control signals that might not make sense, like GPRS to bus 1 and GPRT to bus 2. We'll talk about those, but once we connect all of those up, then our control unit will turn on and off the switches in our data path, and we won't have to. And then we get a fully automatic data path or a CPU that operates on its own with just a start button and a data button.